In this video, we're going to try to explain how molar enthalpy and calorimetry work together. So we've already discussed in another video how the amount of energy that's changing in the reaction is equal to the energy change in a calorimeter, provided we have as close, essentially an isolated system. Isolated systems don't actually exist. But if the reaction happens fast, if the heat transfer happens quickly, if you're not having excessive amounts of heat lost to the environment, it's a good assumption. So in this question, we have a 10-gram sample of propane is burned to heat a 5-liter sample of water in a calorimeter. What is the final temperature of the water if it starts at 21 degrees Celsius? Now, for this question, we need to have the molar enthalpy of combustion of propane. So the molar enthalpy of combustion of propane is negative 2,043.9 kilojoules per mole. And we'll talk about communication later, but this is an enthalpy of combustion. So we say that this is the change in enthalpy of combustion for propane is negative 2,043.9 kilojoules per mole. So that's per mole of propane. Over here, we know the mass of the propane that is being burned. That's going to allow us to calculate the number of mole. So the number of mole times the molar enthalpy is going to equal the change in the calorimeter's energy. So the mass of the water is going to change a certain amount of temperature. We know the initial mass of the initial temperature, but we do not know the final. So in this case, I'm going to calculate delta T, then apply it to figure out what the final temperature should be. So the first thing I'm going to need to do is find the number of moles of propane, and that's mass divided by molar mass. So my mass of propane is 10 grams, and the molar mass of propane is 44.11 gram per mole. Okay, so the number of moles is going to be 0.227 mole. So take that divided by that, and that's what we get. So we have now got the number of moles of reactants that are being consumed. The molar enthalpy we know because it was given to us. And I know the mass of the water. It comes from the 5 liters, so that's 5.0 kilograms. And my specific heat capacity is going to be of water because that's what's being heated. The delta T is what I'm going to calculate. So delta T equals N delta H over MC delta, or pardon me, over MC, right? That'll give me my delta T. So I've just taken this value and divided both sides by it to give me this formula. Delta T equals N delta H over MC. Now, if you think about what N times delta H is, it's going to be the number of moles times kilojoule per mole. That's going to give me kilojoules. So I'm going to have kilojoules up here, and so I'm going to have kilojoules on top, and I am going, if I use kilograms, I would have kilograms here. Well, the kilos will cancel out, which is pretty convenient because I don't want to be left with kilo degrees Celsius. So I'll substitute my values in, and I've got 0.227 mole times negative 2,043.9 kilojoules per mole divided by the mass of the water, which is 5.0 kilograms. Again, the kilos will cancel out, so that's convenient. And then my specific heat capacity for water is 4.19 joules per gram degrees Celsius, so that my grams will cancel out, my joules are going to end up canceling out, my kilos cancel out, and my moles cancel out. It's going to leave me with degrees Celsius. So my delta T is going to be equal to that. And this should come out to 22.1 degrees Celsius. So if that's the change in temperature, your delta T equals temperature initial minus temperature final. So my temperature final is going to be, if I take that over to here, if I rearrange this for temperature final, I'm going to get delta T plus T initial. If you're not exactly sure about it, think about what's happening. This change in temperature is going to increase the temperature because it's exothermic. So my final temperature should be 21.0 degrees Celsius plus 22.1 degrees Celsius is going to give me 43.1 degrees Celsius, and that should be the final answer to my question. But to go back to what is essentially, I guess you probably can't see that, sorry. So to go back to what we initially were talking about, the enthalpy of the reaction here is going to give me a value, and it's still equal to the calorimeter's value. And because of that relationship, we're able to then process this and come up with our final answer, which is 43.1 degrees Celsius. So this relationship is going to be vital to use quite often, and it's what we're interested in with a lot of calorimetry. We're not actually interested in just the energy of the reaction, but more interested in what is the energy per mole of a reactant in any reaction.